All right. It's 2:01. Thank you everyone for joining. We know it's a busy time and afternoon, so thank you for tuning in. This is the first webinar in a month-long series highlighting our California Sea Grant 2022 Graduate Research Fellows. So again, just thanks for joining. We're excited. Welcome. And we'll start off with some introductions, a little bit of background, and then we'll introduce our speakers for today. So my name is Tanya Torres, and I am the Staff Research Associate at California Sea Grant. I primarily focus on marine debris, pollution issues, and I'm also the Extension Coordinator. And so I'll be your host today and your moderator for this series, and I'm accompanied by my colleague Leon, and I'm going to pass it over to her to introduce herself.
Hey everyone, good afternoon. My name is Leon.
Leon, you are cutting out a little bit. If you want, I can give your introduction for you. Apologies for her tech issues, but this is Leon Gua. She is our research coordinator with California Sea Grant and manages all of the pre and some post awards. I'm sure you've seen her name in your emails. But thanks, Leon, for being here. I also see that our director, Shauna, is online, and I might want to ping her to introduce herself and say hello.
Good afternoon, I'm Shauna O, and it's really my pleasure to be here, and I'm really looking forward to learning about some of the work from our graduate research fellows and looking forward to the first webinar. Thanks.
Thanks, Shauna. Thanks for being here. All right, so before we kick it off, I did want to give a little bit of a background. So for those who perhaps aren't familiar with our program, California Sea Grant is a federally funded and university-affiliated organization that supports applied ocean and coastal science for all of California. And we do this mainly throughout our research grants, our fellowships, our extension programming, and some communications and outreach. And so the Graduate Research Fellowship is one type of many fellowship opportunities that we provide. And we provide research fellowships, policy fellowships, as well as extension fellowships. And so if you're interested, you can visit our website to learn more about these opportunities. Someone will put the links in the chat for you. I am aware that our state policy fellowship and the Delta Science Research Fellowship are currently open for applications, and deadlines are soon approaching. So if you're interested, please go check that out. But back to the Graduate Research Fellowship, which we're here for today. This program actually started in 2020. It was designed to directly support graduate students who are working on applied research that met our California Sea Grant's strategic plan focus areas. And these are fostering resilient coastal communities and economies, sustainable fisheries, and healthy coastal ecosystems. And so during the 2-year fellowship, these graduate research fellows are directly mentored by a research mentor as well as a community mentor. And they are to develop an outreach plan as part of their project to ensure that their research is useful for the entities and communities that are invested in their work. And so throughout this month of June, we are proud to feature talks by all of these 2022 cohorts. They want to share all the great work they've accomplished over the past 2 years. So be sure to tune in every Tuesday at 2 p.m. this month to learn about what they've done. And we're going to someone will drop a link in the chat for our flyer, our schedule, and that will also have links to registration in those resources for you. And so that's a little bit of background. We've got 2 speakers today that are going to give about a 10 to 12, maybe 15-minute presentation, and we will have time for Q&A after each presentation. Only 2 today, so it should go by quick. And then tune in for the following Tuesdays for about 2 to 3 presentations each week. So today we've got Jonathon Kuntz and Jim Jacobs who are here. So the first one we'll kick off to is Jonathon Kuntz. His project focused on the anthropogenic impacts on leopard shark ecology with novel applications of stable isotope analyses. So okay, he's got his camera on. Thank you, Jonathon. And you are free to share your screen and take it away.
Sounds good. Thanks, y'all. Like was just said, my name's John Kuntz. and I'll go ahead and share. Oh shoot, click the wrong button real quick. Okay, share, and let's do that. Come on, there we go. Okay, is that good for everybody? Hopefully.
Yes, we see it.
Okay, cool. So, yeah, this talk is going to be, like I said, anthropogenic impacts on leopard ecology with the use of novel applications of stable isotope analysis. And just to get into a little bit of information about leopard sharks in particular, they're pretty long-lived, 24 plus years for the longest aged individual so far. They're pretty generalists, benthic mesopredators that will pretty much eat anything they can. They've got really high environmental plasticity where they can hang out in brackish estuaries, really temperature tolerant as well. And they range all the way down from Mazatlan, Mexico, all the way up. There's been one found in Samish Bay, Washington. So pretty much the entirety of the lower 48 Western United States coast. But here in California, there's two major distinct genetic populations, one in Northern California and one in Southern California, where the California bite is kind of like where that cutoff is. And so I was really interested in the San Francisco estuary population. We used hierarchical generalized additive models to look at San Francisco Bay study data, where California Department of Fish and Wildlife has been going to these 31 original sites from 1980 till present, looking at kind of population of all fishes. I wanted to look at leopard sharks in particular, where we found an overall 77% decline since 1980, where in the Central Bay specifically, there's been a 97% decline in that time frame. So unfortunately, in the San Francisco estuary, there has been a lot of impact to the leopard shark, which can be probably attributed to a lot of direct anthropogenic impacts as well as indirect. And so I'm hopefully submitting this that kind of talks, this paper specifically that talks about a lot of those possibilities in the next month or so. But so this talk, I'm going to kind of talk about how interconnected are the Central California leopard shark populations, and then do they follow similar life history patterns, so we can kind of see if we need to look at San Francisco estuary specifically or the greater population. And so to do this, I looked at 4 different sites where we collected leopard sharks. Down in the South San Francisco estuary, as well as Drake's Estero State Marine Conservation Area, which is a marine protected area, as well as 2 marine protected area adjacent sites, being Tamales Bay and Bodega Bay. And so a lot of these areas are not very far from each other. And so I wanted to see how, like I said, how interconnected are these subpopulations. Isotopes in particular, just to give a quick overview, isotopes are the same element, same number of protons, different number of neutrons, and that changes the mass of the atom. So for carbon in particular, a lot of people have heard of carbon-14 dating. That's a radioactive isotope because it's constantly decaying. Stable isotope is looking at the 2 stable forms of carbon, which is carbon-13 and carbon-12 as a ratio against each other, and that can tell us different environmental kind of processes going on. And so in particular on this graph for carbon and nitrogen isotopes particularly, you can see on the y-axis, delta 15N is nitrogen, what we're going to be looking at. And that's more indicative of trophic level, where the lighter isotope, we as consumers excrete a lighter isotope as a byproduct. So, and for us, it's urea, and because urea or urine is mostly nitrogen, and so as you move up in the trophic level, the consumer's body are holding on to the larger 15N versus the 14N, and so there's a bioaccumulation going on. But there can be problems if you're looking at two different populations where there can be a different jumping off point, a different baseline value. So just because something in one area has a larger delta 15N, one species, than another area, you can't just say it's just a higher trophic level, because there could be baseline differences. So you have to account for those. Where carbon mostly looks at between C3 and C4 plants, where really negative is C3. So you can think of estuarine or almost like riverine sources coming from terrestrial, mostly C3 detritus, whereas offshore is carbon is really positive, or much more positive. So we can look at this as a gradient for movement. And so this is really important in the San Francisco estuary, because there's 38 different wastewater treatment facilities, all pumping in effluent into the estuary after some type of kind of cleaning process. So some completely nitrify their water, which is turning it from ammonium to nitrate, and then partially denitrify, which is sending N2 in the form of gas. But so in these green pluses, those are wastewater treatment plants that are sending out only water with nitrate from those wastewater treatment facilities. That nitrate is really high in delta 15N, which affects the baseline that particular organic matter can kind of be influenced by. So whereas all the kind of yellow minuses are pumping out ammonium, which isn't as high. And so you can actually see, I've been going out with the US Geological Survey, where they have, I think, 38 different stations that we go to with a flow water system. And I take particulate organic matter samples seasonally. And so I'm going to hopefully use a hydrodynamic model to turn this into an isoscape and have almost a full heat map of the entire estuary of delta 15N values. But this is just showing what we found so far. We're down in the South Bay, particularly where I caught leopard sharks for this study, is really high in delta 15N, so probably affecting that baseline. And so here is showing a lot of leopard shark different tissues. Different tissues will tell us different time scales, because there's different incorporation rates from eating, ingesting prey items, how long that takes to actually be incorporated into a specific tissue. And so first, we're going to look at muscle, which pretty much tells us the last year, roughly, of life history, where we can see that, at least in carbon specifically, the lower South Bay and Tamales Bay are pretty distinct from Drake's Estero and Bodega Bay, which is really interesting, with Drake's Estero, Tamales Bay, and Bodega Bay being so close together. If there was movement going on between sites in the last year, you would expect all of them to be the same or very similar. But the South Bay and Tamales Bay, actually, because they're more estuaries, they're getting a freshwater input, which is bringing more of that riverine, really negative carbon. Whereas Drake's Estero and Bodega Bay don't really have a riverine input, and they're facing south. And so that the California countercurrent is bringing kind of offshore carbon into those embayments, which are affecting leopard shark muscle tissue. And so for nitrogen specifically, we're also seeing kind of Tomales Bay, Bodega Bay being pretty similar, Drake Estero maybe a little higher, but the South Bay particularly being having a huge range, much higher. So possibly seeing that these leopard sharks might be affected by that baseline, that wastewater effluent. And so when we look at them together, we can start to see that they're starting to partition out. Whereas in the last year, there might not be as much actually movement in between these places. So possibly looking at them as their own subpopulations. And so I also wanted to look at just not one particular time point, but eye lenses and vertebrae. Vertebrae have been used for a while, but they make bands just like trees do, so you can age them yearly bands. And so you can look at the isotope values across those yearly bands to get a full life history. Fortunately, vertebrae are really hard to work with. And so eye lenses have actually kind of been started to use since 2014 in mostly teleost fishes or ray fin fishes. But no, very few have tried to work with it in sharks, and no one really has been successful yet. And so we wanted to try to get this tissue to use in sharks. And so you can see here where on the left you have the eye lens that makes layers, kind of like an onion, where I can go back and peel each layer to get a full life history. And that can be similar to the layers of the vertebrae on the right. And so looking at leopard shark eye lenses to vertebrae for Delta 15N over on the left, they seem to be tracking pretty much the same thing other than some variation. Whereas carbon on the right, you can see that they're tracking the same thing, but there is somewhat of an offset, and we call it a discrimination factor. Whereas the islands and the vertebrae are just taking up the isotopes, kind of, we call it being fractionated, but changing the isotope composition slightly. And so we can see that this is kind of like how I peel the eye lens. So all the way at the smallest on the left is birth, all the way to death. And we can look, I record the diameter of those eye lenses. And then I will pretty much put that diameter, because the diameter of the shark to the total length of the diameter of the shark eye lens to the total length of the shark is pretty much a 1-to-1, an R-squared of 0.97. We can then put that into a von Bertalanffy growth model to pretty much say, okay, at what size of the eye lens it was, at what age was it at that time. And so looking at particularly Delta 15N for those different sites, I was actually peeling way back further in time than I thought. And I was actually peeling back into the embryonic stage where they're gestating in the mother's stomach. And because technically babies are feeding off the mother, they're actually at a higher trophic level. And so you can actually see during the embryonic stage, the babies taking on the mother and actually mother's tissues and becoming a higher trophic level than them. Then once they're born at age 0, they kind of go and take on the isotope value of their habitat. And so you can see that a lot of them are following the same pattern. It's just that the lower South Bay, that top blue one, is a bit higher. So thinking that it is that baseline change. And for carbon, which is really interesting, it's much more differentiated, where you can see the lower South Bay all the way at the bottom is pretty stable. So thinking that sharks in the San Francisco estuary that were found there might be staying there their whole lives. Whereas it looks like also that the San Francisco estuary, because there is all kind of the same jumping off point at that age 0, the San Francisco estuary might be populating the rest of these areas, where at a young age, they're moving out and then choosing a certain habitat to live in, be it Bodega Bay, Drigstero, or Tomales Bay, and then staying there. So kind of conclusions, possible leopard shark subpopulation distinguished by stable isotope analysis in muscle. Eye lenses are a valid chronological tissue for stable isotope analysis in sharks. And leopard sharks in the San Francisco estuary may be staying there their entire lives. So with those huge declines in leopard shark population, we might need to start looking at the San Francisco estuary as a unit of conservation. And with that, I'll take any questions.
Thank you, Jonathan. Yeah, if anyone has any questions, feel free to raise your hand or add them into the chat or the Q&A, and we can have some dialogue with Jonathan here. And if there aren't any at this moment, feel free to reach out with any questions. Oh, we have one from maybe Leon.
Yeah.
Can you hear me okay?
Yes.
Yep.
Okay, great. Thanks, Jonathan, for your talk. I was curious who your community mentor was and how they or other organizations might be using your research outcomes.
Yeah, so my community mentor is Jim Hobbs, who is with California Department of Fish and Wildlife. He is heading the San Francisco Bay Study down in the San Francisco Estuary region headquarters. And so they're kind of, because I'm using San Francisco Bay Study data, he is kind of on this paper that we're hopefully going to be submitting in the next month, looking at these population declines and kind of why leopard sharks are declining in the bay, which could be a multitude of different things, and hopefully turning that into policy later on. But that policy, right, might not change until it actually gets out there in the hands of policymakers. And so Jim Hobbs is very much has been a big part of a lot of court cases recently, most notably for the listing of Delta smelt back in the day, and then also now the longfin smelt for the Endangered Species Act. That's ongoing. I think the longfin smelt right now, but hopefully kind of get the ball rolling on at least some protections for the leopard shark here in the San Francisco estuary.
Great, thank you. Were there any other questions for Jonathan? Well, Jonathan, if you might want to stay on the line, if any come through on the chat or anything, feel free to answer those. We can go ahead and move on to our next speaker. Thank you so much. So next up, we have Jim Jacobs from the University of California at Santa Cruz. He will be presenting on his project titled Quantifying Sea Level Rise Effects on Critical Coastal Wastewater and Transit Infrastructure in 2 Low-Income Residential Developments at the San Francisco Bay, California shoreline using hydrogeology and geochemistry measurements. So take it away, Jim.
Okay, you can see the screen all right?
Yes, we can.
Okay, so I'm going to talk about urban settings where sewers may become preferential pathways, or certainly the utility trench. And so just to give you an idea, if we're out in the rural area on the left side, that's conventional septic system. So even though sea level rise might affect somebody living on the coast in this situation, it may not necessarily increase flooding risks. Whereas on the right side shows example of a sewer line which might leak, and there might be a utility trench that the sewer is in, which might have higher permeability than surrounding sediments. Because the waters may go in there from what we call a highest astronomical tide, or colloquially called a king tide, those waters may move preferentially in those locations and all of a sudden pop up somewhere that we aren't expecting and cause more surface flooding than if they hadn't been there. And on the lower right just shows a map of a typical urban sewer area. This happens to be Atchison Village, which is one of the areas I worked in, but it just shows that the network is massive, and it's all connected. So if we start getting massive inputs of water, whether it's high groundwater or if it's overtopping marine water, those waters could go through these systems and all of a sudden show up somewhere else. So it's kind of an important aspect of urban flooding relating to sea level rise. So let's look at extreme events. At the present time, we look at what NOAA has provided, and this is from Suite 2017. He's with NOAA, and it's basically the sea level rise, and it's in meters on the left side, the black area, and then there's different scenarios that the NOAA and USGS and others have come up with. This happens to be NOAA's interpretation, but predicting the future is a really difficult area of endeavor. So if you're a city planner and you're looking at a particular local space, maybe a vulnerable community, how do you address this? Which color do you pick and say this is where we're going to be? Because it's kind of difficult. So I've been suggesting that instead we need to go back the other way and start looking at the local area and then sort of working out how that fits into the more regional predictions from NOAA, USGS, et cetera. This happens to be from what we call a king tide in Mill Valley, just north of San Francisco. It's on the bike path. So there's basically two extreme events that we see in the last year or two. One is the atmospheric rivers on the left side. And during the year 2023, we call it water year, where it starts October 1st of 2022, goes to September 30th. There were 15 such extreme events or atmospheric rivers. On the right side shows the Holiday Inn Express in Mill Valley, where there's a storm drain, and because we have these king tides, the water comes backwards because they don't have a flapper valve on their storm drain, and then of course flood the parking lot when the tides are very high. And so the processes associated with sea level rise and groundwater flooding are shown here, where we end up with not only heavy rains, but we may have excessive high tides, which are an astronomical phenomenon, but we also end up with groundwater flooding and stormwater backflow. And so this is from NOAA, from the Suite 2022 report. It just shows you all the different flood processes that could impact an urban area. And so one question is whether we can use groundwater in the utility trenches just to see how that's going to impact infrastructure vulnerability as an indicator. And one good thing is that the material in those trenches doesn't change. So every time we have water coming in, the response should be pretty similar. And so these are some of the main flood processes. You can see the different directions. So this is my diagram basically showing what the area looks like in Manzanita, where we have the Younger Bay mud. It's wetland deposits. It's a plastic clay of the wetlands. And then over the last 100 years, people have in several different steps filled it with artificial fill. Now the fill, some of it's road base, which is basically gravels and sands, and that's in the area near the roadways as well as the railroad. But then there's other areas that are mixed with the gravel plus some of the clay, and they drain very poorly. The areas in blue, the blocks that are in blue are some of the areas that I use for the data. I have the atmospheric river from the weather station. I have the highest tides from NOAA and my own tidal gauge. And also I have groundwater because I installed a large number of wells to measure that. On the right side, because it's artificial fill, we end up with possible coastal erosion and land subsidence, as well as groundwater pumping. Pumping reflects when the water's flooding a lot. Sometimes engineers will put pumps in there, but in the process of putting the pumping, the sediments compact, and then you get more subsidence. And if we look at the flood processes in terms of the time scales and magnitudes, the ones that I'm the most interested in are the ones that are also the shortest, in terms of we can evaluate what the water levels are in the subsurface, like in utility trenches, by putting wells in those, and we can see that if we have an extreme tide, a high tide, or an extreme storm like an atmospheric river. Storm surge hasn't been a big issue in the study areas that I've looked at, but can add a fraction of a meter if it's coming toward the shoreline. So what are preferential flow pathways? So basically on the left side, you have basically sewer trenches, utility trenches that are filled with pipes or conduits, electrical conduits. And when they were laid down, frequently, sometimes there might be sediments there that will allow water to move through them more easily than in the surrounding sediments. Likewise, of course, I show here a buried oil spill. If there's contaminants, as the sea level rises and groundwater rises, that may end up mobilizing and all of a sudden spreading these contaminants to other locations. On the right side, we see a preferential flow pathway as a stream channel, and that's a naturally occurring one. But nonetheless, if you're in an area that has a sand channel, you're more likely to get water to run through there more easily than if you're in a clay lens off to the sides. And so here's an example of preferential flow pathways. Here's a house. This is from Ontario. And if this was brought to me as a hydrogeologist and I see groundwater is just below the basement and we have basement flooding, I would say it's likely that groundwater level has risen and all of a sudden we have basement flooding, in that case, you'd probably put a sump pump in, turn it on, and then you remove the water and lower the groundwater table. But in actuality, that's not what happened here. And it turns out this is the rest of the story, where because of series of the creek and the stormwater backflow going into street drains, and then there's tile drains from the house, you end up flooding through a series of preferential pathways into the basement. And we're going to have to start thinking of these concepts of these preferential pathways and with regard to building flooding and even surface flooding, because sometimes it's not just groundwater pushing up into the basement, but it could be something related to drain backflows. And so we'll look at sea level rise, that's SLR, artificial fill and preferential flow pathways. And so part one, I'm going to just talk about how we measure conductivity, water level, and temperature. That's the NOAA grant. And then I also used, try to determine mixing zones by looking at stable water isotope and major ions. And there's mainly three locations. If anybody's familiar with the Bay Area, Manzanita and Tamalpais Valley are just north of Sausalito, north of San Francisco, the Golden Gate Bridge, if you know where that area is, in Marin County. And the third one is Atchison Village, which is in the city of Richmond in Contra Costa County. And so the right side shows Manzanita with the star, but the other two sites are located there. One aspect of the diagram on the right shows that there's a lot of historic wetlands since the 1800s that has been filled in. And as such, the model on the left is for Manzanita, but basically we have this Younger Bay mud, these clay deposits, and then we have fill on top of that. And I put my wells into the artificial fill to see how much the water is moving through the fill. I'm also interested in what happens in a utility trench within the fill. Is it going to be a preferential pathway and all of a sudden cause flooding in areas that we didn't suspect? So here's a historic map of Manzanita Point in 1851. You can see that we have the bedrock headlands off to the left side in the upper left drawing there. And then the rest of it is basically wetland deposits. You see some ancient, the historic channels there. You can see those. But for the most part, it's mostly just wetland clays. In 1930, they removed some of that headlands, the rocks, and they filled in the some of the wetlands, and this is from 1930 when Caltrans was putting off the first bridge across Richardson Bay there. And so they filled in the area with well-draining rock. So some of the fill has that well-drained rock in it. By 1940, we have more fill going in, and they have engineered drainage channels as well. And the Franciscan bedrock, which is the source of much of the fill, has been reduced in terms of the bedrock it's moved. They've cut a significant amount of that bedrock away and quarried it for the fill. And then finally, this is 1990s. All the filling that has occurred by this point. Coyote Creek has been basically an engineered drainage channel, comes into Richardson Bay, and Manzanita is basically the marsh that is the intersection of the bike path, which used to be the railroad grade, and then the Highway 101 bridge. That's in the lower right corner of the photos. So here's my little cartoon of the conceptual model where we have the bedrock underneath it all, and then we have the older and younger bay mud. The older bay mud's probably about 150,000 years old, and the younger bay mud is about 10,000 years old, and that represents when there was a wetland there. Since then, about 3 meters of artificial fill have been deposited, and we have a shallow groundwater table there. It's more what I call a perched. It's not an unconfined like aquifer, but rather it's a perch zone, but it is unconfined. And within each of the sewer trenches, we also have water in those, and I'm still evaluating that data. So when we have a strong rain, the rain comes off to the right, upper right there, goes down the hill, and then enters the fill, and it moves along the top of the younger bay mud and just sort of sits there. And that's how we get flooding in this area. And so how does groundwater respond to extreme rains? I'll look at that in a minute. Anyway, so I installed one well, monitoring well 1, MW1, in the utility trench, and I'll show you how I did it. And in this particular location, I have 6 other wells installed at various distances from preferential pathways. So my prediction, my hypothesis is that wells in utility trenches will be closer to the preferential pathways, that's the utility trench, and they will also show a higher level of groundwater elevation when we have a key event such as an extreme rain like an atmospheric river or these king tides. And the wells that are further away from the utility trenches or preferential flow pathways will have less of a response. This actually shows monitoring well 1 when it was flooded from a king tide. And anyway, so the method was that I installed 7 wells that were up to 3 meters deep. I tried to keep the wells within the artificial fill. I installed data loggers that were recording water temperature, water level, and electrical conductivity, and they were recording it every 15 minutes. And I also took readings during 6 sampling events of dissolved oxygen, ORP, that's oxidation reduction potential, pH, conductivity, temperature, and turbidity. So I could then compare the readings from the data loggers with the readings that I got in the field. And this is showing where I put monitoring well 1. A force main is basically, there's a sewer pump on one end of on the left end of this diagram, pumping up the sewage along that pipe, but after the pump shoots out the sewage, it then flows by gravity. This particular force main was repaired in the mid-90s and is HDPE, high density polyethylene plastic, so it's not likely that it leaks at this point. There's also a gravity sewer main, which I also wanted to get some wells near those as well. But MW1 is literally in the utility trench, and it's about 2 inches from the sewer line itself. And so here's the conceptual idea of what I was trying to do. There's a sewer pipe there. We had artificial fill, and I put the well in, and it's only, I say, about 2 inches away from the outside of that pipe. You ask how I did it. I certainly didn't use a big drilling rig. It turns out that the sewer agency was planning to figure out where their pipe was because the maps from the 50s were not available. They had to use the method of using high pressure air and trying to, it's called an air knife, to try to locate the pipe once they located the pipe and we knew exactly where it was, then I installed a well next to it. And that's how it was done with this. It's a vacuum truck and it's called an air knife. And I installed a well right next to it. So I could determine if water is moving through, preferentially through the utility trench. I also installed some other wells. The red wells where the boring logs and wells are in red are the ones right in the trenches. The blue ones are a little further away. And then we used a geoprobe to install the other wells. And this just shows one of our geoprobes working. And this is what the rocks look like. It's a plastic clay in the upper photo there. And within there, there's angular pebbles, which are from the hillside that were mixed in when they laid down the artificial fill. I had a Solens level logger 5 in each of the wells. And then I also had a barrel logger to compensate for barometric pressure changes, so I could compensate the data. Anyway, so this is what the fill looks like in the upper portion of the slide. This is the sort of a lithology of the different wells. It's all mostly artificial fill, and the well construction is on the right side. And so pretty much we're getting our wells right within the artificial fill zone. And then I put a well about 10 meters or about 30 feet away from MW1, MW5. It's also in fill, but it's not in the utility trench, so I can make a comparison with it. And I put sensors in both of these wells. At the end of the day, I determined there was 27 days where the tides were over 6.5 feet or 2 meters. And that's when we basically had most of the flooding. And there were 15 days that were considered atmospheric rivers by NOAA in this area. And just to show you what atmospheric river looks like on the left side, these are these massive, typically storms coming out of the Pacific, and they're just massive. They come in and they may be several days like that. We had 41 days where there was rain that was over 1.3 centimeters per day. So that's quite a bit of rain on the, so that's extreme rains. On the extreme tides, we had 27 days where the tides were over 2 meters. And you can see the highest astronomical tide, the HAT, is shown with the red lines. And so here's the area of Manzanita. Just showing you some of the other data. We have a Coyote Creek tide gauge over here. It's off to the left side. And we have a Sausalito NOAA tide gauge. So I can compare my tide gauge, but I put my own tide gauge in here as well, where the tide comes in every day. Twice a day. And then I do the comparison so that during the king tides, we end up seeing similarity between my tide gauges as well as the NOAA and the Coyote Creek tide gauge. And then over here, when we have these extreme rains, these atmospheric rivers, we notice that the Coyote Creek and my tide gauge show a difference between that and the NOAA tide gauge. And the reason is that the difference there is the runoff itself. So that is the runoff from these extreme storms. I also looked at the response within the actual wells between my tide gauge, let's say, and a well that was not that far away, only 0.4 meters to the high water line. So it's very close to the tidal channel. And the tide gauge is shown in the upper right here, and it peaks. At this point, the peaks are pretty similar, but the starting point is different. So MW4, there's almost 3 hours lag time between the start of the rise of the tide versus when it actually goes into the well. So these wells are in areas where the clay is pretty impermeable, and you're not getting a lot of movement into the artificial fill from the king tides. By the time you get out into the utility trenches where MW1 is, you have a little bump here, but it's not very significant. On the left side just shows in Portugal as an example where you might have in a good clean sand, you might have admittedly it's attenuated in the groundwater, but you do have a phase shift between the estuary and the groundwater, even though groundwater is significantly lower in terms of the peaks. So we did see some of that. So if we take all the data that I have, this is the kind of data that I get. It's the tide gauge. Here's the precipitation in the top line. And then I add the different wells and I can start comparing them. And of course I have it in a digital form, but there's some interesting aspects. One is that these two, MW7, MW1, are in the preferential pathways. And so you end up seeing a lot more motion there, suggesting water's moving in and out a little bit more versus MW5, MW3, and there seems to be a little bit smoother. There's not as dynamic as the MW7 and MW1. And here, if we look more carefully, we can see some very interesting. Here's an extreme tide. What we're seeing here is that the tide comes in MW1 at the bottom, where the oval is here. You see the jump in conductivity. That's basically the seawater infiltrating into the well through the soil. And so conductivity goes way up, as does the water level, and the temperature drops because the water coming in is much colder than the groundwater. Likewise, for an extreme rain, we see a dip in temperature because the rainwater is colder than the groundwater, and the conductivity drops because all of a sudden we're seeing the salt content of the water in the groundwater dropping because we get an influx of fresh water from the rainwater infiltrating into the well. This is the day, that particular day, where the seawater is coming over, and there's the well. It's a circle right there. We're seeing stormwater backflow on the right side as well. Just to give you an idea of my method, in which I haven't completed all my activities, but basically I look at the tide, which is, for example, in the upper left, I see the point of rise, peak tide in the fall, and then I look at the extreme rain, the same kind of thing. And then I look at the groundwater response, which is number C at the lower left, where I have the start, the peak, and the end, and then I compare them, and I can then see what the lag times are and how much motion we're seeing in the groundwater versus these particular extreme events. And when I plotted up where the distance to the nearest preferential pathway versus the groundwater elevation, it turns out that the response is pretty close, so that basically the wells in blue and yellow are within the utility trenches and are preferential pathways. In other words, water's moving there preferentially versus the other wells, and that matches the model that I proposed. Not exactly perfectly circular like my original hypothesis, but it came up pretty close. Just want to show other evidence in this location. We have backwater flow in the storm drain. We have the flow coming near the surface. We have land subsidence, which we've documented. We also see emerging groundwater as the water is coming up very close to the surface. This just shows in the groundwater that during that period of time between November and July, water was within a few inches of the surface, which is really truly amazing. There's no place for that water to go if we were having an extra storm. We don't have a lot of room to store that water. So this is showing where the sewer line is brown. And so there's a utility trench coming right through here. And the wells that had zero ability to take more water were MW1 and MW2. And when we have emerging groundwater, the location was right there. And this is the model where the groundwater rises, it comes to the surface. And here's we have it. You can see it right here. That's the emerging groundwater. Here's the tidal inlet, that's salt water. And so here's the utility trench going through. And interestingly enough, when I measure the water depth in MW1 and compare it here, MW1 is slightly higher. And when I test the water over here for salinity, it's fresh water. It's not salt water, even though the tidal inlet's right here. So we're saying the groundwater is coming to the surface and flooding. And this is a reflection that it might end up in a situation where we might start seeing this water coming out in places that we didn't expect. So these are my conclusions, that we're trying to establish baseline conditions, and we noted that the groundwater response on average in the utility trench was about 2.8 times higher than in non-utility trench areas, non-preferential path locations. Given that I have a few more minutes, I'm going to probably just go to just call it quits here, if that's okay, and be glad to take questions rather than go on too much. Is that okay?
Yes, thank you, Jim. Thank you for all that information. Are there any questions for Jim? Let's see, I think we do have a question. All right, so do you think that the runoff during atmospheric rivers is bringing anything different for example, bacteria, viruses, etc., into the estuary than normal runoff.
Okay, yeah. I don't know about the bacteriology of that. Certainly, it comes through very quickly. Frequently, it'll sit around for a while on the surface in the sense of the ponds until it drains out. We have, unfortunately, okay, so the king tides are about, it stays high for between 2 or 3 hours before to 2 or 3 hours after. So you get about 5 or 6 hour window of peak tide. If we have an extreme rain hitting at the same time, or I should say draining at the same time that we have a king tide, all of a sudden we're going to have like twice as much water that we normally have. That'll be interesting, although maybe not a great thing for the communities involved. But yeah, that's the problem. I don't know about the bacteriology. I don't know that, but it's certainly having more water flushing through all of a sudden might create some interesting situations.
Thank you. Are there any other questions? Perhaps while I wait, I had a question. I'm just curious in these, while you're, in these areas and gathering these data, like how much does, debris or trash pollution kind of affect these flooding areas? And if that played a big role or if you've seen or not.
Actually, that's an excellent point. We have had stormwater backup, and in Atchison Village, one reason was that the drainage areas were not complete. They were blocked, and they eventually did the maintenance, and now they work fine. But if you're not doing your maintenance, or if your storm drains are plugged up either at the surface where the grate is, or in the actual the stormwater drain box, utility box, or within the pipe itself. If it is, then you're not being able to use the full capacity of the pipe storm drain. And so it's more likely to flood. So maintenance is a really big part of sea level rise protection, because we're not using the storm drains that are existing because they don't have flapper valves on a lot of them. I'm not sure why. I guess for so long, sea level was never as high as it has been. So up to now, we haven't had that problem, but now all of a sudden we're starting to see water going backwards. And secondly, maintenance hasn't been a big deal because we haven't had flooding as much as we are starting to see. And so cities and counties are going to start to have to, or volunteers will have to start picking up trash to make our infrastructure work better. I can make a plug. My wife works with Caltrans, and they actually do clean up at Manzanita actually every month, trying to pick up the trash. And I think that helps a lot, because when you get a lot of trash within either the storm drains or in the drainage ditches, whatever, all of a sudden they can't function properly.
Yes, it's a very big issue, I know. We've got about 5 minutes left. If there are any other questions, feel free to raise your hand, come off on mute, or just enter it into the chat. We've got our 2 speakers still here that can answer any of your questions for you. But if not, no one's going to be opposed to ending early. I'd love to thank our 2 speakers, our first speakers. Thank you so much. And again, reminder that this is the first webinar in a month-long series. Every Tuesday this month of June at 2 p.m. Please tune in to celebrate and hear from our 2022 cohort of our graduate research fellows. Yep, the full schedule has been dropped in the chat along with the registration link. So please share widely with your networks. We would love to encourage everyone to come and hear from our fellows. So thank you so much. And if you have any questions, please reach out.